Okay, in today's lesson, we're going to talk equilibrium. This is going to be our first lesson that introduces equilibrium. Although you have had some experience with equilibrium in the past, today we'll go into more detail on the third and final type of equilibrium. So our learning objectives for today would simply be to describe equilibrium in a chemical reaction in terms of reaction rates and in concentrations. And we'll save Le Chatelier for tomorrow's lesson. This is a great little introductory video that you would definitely want to check out. It shows a great example or analogy of equilibrium. It's on the regular presentation and several minutes long, but check that out. We're going to skip it right now. A good way to describe equilibrium is simply a state of balance, and there's been several types of equilibrium we've already discussed this year, like phase equilibrium, dissolving equilibrium with a saturated solution, and we have already at least touched on chemical equilibrium with acids and bases, weak acids and weak bases. Here's a quick little analogy. When airlines used to actually fly planes in the air still, and not just for packages, Southwest, they used to fly this route, Los Angeles to Long Island, New York, and it would never be a direct flight. Instead, we'd take off from Los Angeles, usually land in Las Vegas, where a bunch of smiling faces would leave the plane. I'm not sure why they were smiling so much. And then a bunch of frowny faces would get on the plane. And then we continue on our journey, sometimes stopping a second time or just going all the way to Long Island. Anyway, the point is, during however many times we stopped, people would get off the plane, but roughly an equal number of people would get on the plane, different people. And so if you just look at the number of passengers on each leg of the journey, it looked like there's no difference. Just people, same amount of people from Los Angeles to Long Island. However, there were different people. We know that there was change that happened as far as who the people were, but the numbers were the same. And that's kind of the same thing that's happening with equilibrium. There's change happening, but there's also things that are equal. Here's an analogy that is also still set up, something similar, still set up in the classroom. Last I checked, we had the closed water bottle and the open water bottle. They both started at the same level. I forget when we actually set that up, but I put a little marker to show where they both started. And the closed water bottle still has the same amount of water right at the line where I marked it. And it's going to continue to have that until someone opens that, hopefully not. But the open container, the level of water in that open container has decreased significantly at this point. And it's going to start speeding up now that now that it's getting warmer and probably the air conditioning isn't kicking on in the classroom since we're not in it, because of the virus. Anyways, closed container versus open container. Closed container is really what we want to focus on, because in a closed container, it's very tempting to say, hey, the evaporation stopped in there. But that's not true. Remember that? We said evaporation never stops. It continues. It's just counteracted by an equal amount of condensation. So the rate of evaporation is equal to the rate of condensation, and therefore it looks like nothing's happening. But that's phase equilibrium, when those rates are equal. Same thing is true with what we'll call dissolving equilibrium in a saturated solution with excess solute on the bottom. That excess solute is very tempting, again, for us to say, well, it's just sitting there. The amount of solute on the bottom hasn't changed, so nothing's happening anymore. It stopped dissolving, right? No, it did not stop dissolving. It always dissolves, just like we always have evaporation. We continue to have dissolving. It's just that it's counteracted by an equal amount of recrystallization. So it looks like nothing's happening, but really, again, these things never stop. Crystallization happens at the same rate as dissolving. It's the rates that are equal when we're at equilibrium. Okay, which brings us to chemical equilibrium, and this is what we focus on for the rest of this unit. Some reactions, as we saw with a weak acid or a weak base, some reactions simply are reversible, right? You start making products And as you make more and more products, suddenly the products, it's like they're traders. They go and collide with other products and then undo all that work you just did and form reactants again. Really, though, keep in mind, none of these things have like a will or a desire to do anything. They're just randomly colliding. Bonds get broken, new bonds are formed. That's all there is. So it should not trip you out to think about reactions being reversible, because it is all about random collisions. Product molecules, as you get more and more products, you get more and more collisions of the products. So it's more and more likely that those products could collide and break the existing bonds that form the products and form the new bonds, which were the original bonds of the reactants. All right, here's the classic reaction. There's a lot of history to this reaction. Check it out. It's not all positive history. This goes to chemical warfare kind of history. But anyway, this is a very important reaction, nevertheless, of nitrogen gas reacting with hydrogen gas to form ammonia gas. And that ammonia gas we use for all sorts of things, from explosives to fertilizers, which have transformed how we make food, how we farm, factory farming and such. We need fertilizer for factory farming. Anyways, but once you have ammonia, turns out ammonia, when it hits other ammonia molecules, can just reverse the reaction and turn back into nitrogen gas and hydrogen gas. So this is a totally reversible reaction, and you can manipulate things. We'll look at that later, the next two lessons. But essentially, we're going back to kinetics here when we look at reversible reactions. So as you proceed with a reaction, a forward reaction, the nitrogen and the hydrogen gas reacting, as you start using up the reactants, the concentration of those reactants decreases. And we saw with kinetics, if you decrease the concentration, you're going to slow down the reaction. So the rate of the reaction slows down as you proceed, right? Because the concentration of the reactants are decreasing. At the same time, because this is happening in the same exact location, you're creating products in the same place. So you've got reactants bouncing around, hitting each other, and now you've got more and more products bouncing around, hitting the reactants and the products. For reversible reactions, again, not every reaction is reversible, but many are. But for reversible reactions, the reverse reaction where the products hit other products and then kind of reverse themselves, that happens more frequently as you get more and more product. So at the same time the forward reaction is slowing down, the reverse reaction is starting to speed up. At some point, they meet somewhere. It's not in the middle, probably, but they're going to meet somewhere where the rates are going to be equal, and that's where we're at chemical equilibrium. Here's a way to graphically show that. All the way on next to the green arrow here at the starting point of the reaction, we have a lot of hydrogen gas and a good amount of nitrogen gas, but virtually no product NH3. But as we proceed, you start using up the reactants really fast. It's a really steep downward slope, and we start forming products pretty quickly, but it doesn't continue on that same linear trajectory. It starts to level off, or we can call it flatten the curve. Anyways, why is it flattening? Well, because again, this is happening in the same chamber. First, you went really fast using up the reactants, but now as the reactants become less and less concentrated, you slow down this forward reaction. And as you get more and more products, that will enable the products to start reversing the reaction and starts to speed up. And at some point, somewhere where everything's all flat, that's when we can say, not that the reaction has stopped either direction, they don't stop. Instead, they have met where the rates are going to be equal to each other. The forward reaction is balanced out by the reverse reaction, somewhere around here, I think. That's where it's kind of started to be all constant. Same concentration of nitrogen and hydrogen and ammonia. Everything's constant. But again, the reactions didn't stop. They just counteracted each other. The rates were equal. That's why. So that's what we could say. At a chemical equilibrium, again, it's a state of balance. And the thing that's actually equal, just like in the other two examples, is the rate. The rate of the forward reaction is equal to the rate of the reverse reaction. Reactions never stop. They don't get to equilibrium and be like, all right, let's call it a truce. No, they just keep going forever until you change something. All right, what about the concentration? So the rates were equal. Does that mean the concentration should be equal? No. They are constant. That's what we saw on the graph. None of those lines were all matched up. They're all three different. Watch, let's go back. See? All three different concentrations, but they all stayed constant. That's when we were at equilibrium. Another way to look at it, I would draw this on the board, but instead I drew it on a piece of paper and took a picture. Here it is. So this fictional reaction with A and B reactants forming C and D products. At the start, all we had was reactants, 100% reactants A and B, 0% products C and D. After 1 minute, this is a quick reaction. After 1 minute, we've already knocked out a quarter of our reactants. 75% only is left of our reactants, which means 25% has been turned into products. And by the way, notice the arrow, the double arrow showing us reversible reactions. So that was after 1 minute, we lost a quarter of the reactants turned into products. After another minute, it's not a second quarter, because remember, we slow down as we go, as we're reducing concentration of reactants. So after another minute, we lose about 10%. So we went from 75% to 65% now reactants, and now we're up to 35% products. 2 minutes has gone by. Another minute goes by, we're down to only 60% reactants, 40% products. We wait another minute, and it's the same. 60% reactants, 40% products. Nothing's changed between minute 3 and minute 4. So what does that tell you? Have the reactions just stopped? Hit the pause button? Taken a break? Kicked back? Went into isolation? No. They reached equilibrium because the rate of the forward and reverse reactions equaled each other right around the 3 minute mark. So then the concentration of reactants and products are held constant. They're not changing anymore because the rates are equal. So that forward reaction wasn't all that great. It only formed 40% product before it leveled off to being equal to the reverse reaction. But, sometimes that happens. All right, so notice what wasn't equal, the concentrations. We didn't get 50%, 50%. That's not when you're at equilibrium. You're at equilibrium when the amount of reactants and products are constant. They stop changing, and then the rates are equal. Okay, so I don't know how many more times I can say that, but hopefully that was enough. Here's a nice little video too. It's a little visual. It's a good little visual. It's fun. Watch that on your own time when you look at the presentation if you'd like. So just to see if we learned what we were supposed to learn, see if you can answer these 3 questions. For a reaction at equilibrium, we're talking about a chemical reaction at equilibrium. Number 1, what can be correctly assumed about the rate of the forward and reverse reaction? Maybe reactions, I should say there. Number 2, what can be correctly assumed about the concentrations of reactants and products? Again, when we're at equilibrium. And number 3, at what point will the reactions stop? Pause, see if you can answer these, maybe write them down so you can't cheat and say, oh yeah, that's what I meant. You know what I'm saying. Pause it. Okay, unpaused. Let's see if you got the answers right. Number 1, what can be correctly assumed about the rate of the forward reverse reaction at equilibrium? Well, when you're at equilibrium, that means the rates are equal. So the rate of the forward and the reverse reactions are equal at equilibrium. Number 2, what can you say about the concentrations of reactants and products at equilibrium? The concentrations will be constant, not changing anymore. That's what you can say. If you said they would be equal, you're wrong. Incorrecto. And number 3, at what point will the reactions stop? Just like the Terminator, the reactions never stop. They just keep going and going. When you're at equilibrium, there's no pause button. They just keep going. They keep going. All right, so these were our learning objectives. We were supposed to describe chemical equilibrium In terms of reaction rates, right, rates are equal. And in terms of concentrations, concentrations will stay constant. So hopefully you understand that. You should be able to now answer the questions on equilibrium intro, just that side that says equilibrium intro questions, not the equilibrium summary side. That's for later.